Welcome to Pre-Calculus. Today we will investigate solving right triangles on the coordinate plane. We'll take a look at two examples. Our first example has the right triangle ABC, and it's situated on the coordinate plane with basically no marked information. I do not know side lengths, and I don't know immediately what the angle measures are. So I've got to solve the right triangle by finding all 6 of those pieces of information. I need to know the 3 side lengths. I also need to know the 3 angle measures. Well, I can use the orientation of this triangle to help. Notice that it is got 2 of its sides that are either vertical, like side AC on the left, or perfectly horizontal, like side BC on the upper part of the right triangle. And I really can count. Anytime I've got vertical or horizontal sides, I can just count. So for this side AC, I really am going to use the vertices here. Let's give myself the coordinate -5, comma, -5. And vertex C here's at -5, +5. So really, in terms of counting, I'm looking for the distance between -5 and 5. So from -5 to 0 is 5. From 0 to 5 is 5 more. So side AC has a length of 10 units. So I'll mark it there on the side. I'm also going to mark it here on the diagram. Side AC is 10. And I'm really helped by that because notice my X values are fixed. That means that's a perfectly vertical line. As we observed at first, we can do something similar with side BC here. If that's got the coordinates 2, 5, there I'm really looking at the X values. So from 2 back to 0 is 2 distance, 2 units. And then from 0 to -5 is 5 more units. From 2 to -5 is a distance of 7. So I see here BC has a side length of 7 units. We'll mark that on the diagram as well. To find the length of side AB, though, defies my strategy of counting because it's not perfectly vertical, not perfectly horizontal. It's at an angle. So there's no way for me to very easily count the units on side AB. But because I am in a right triangle, I know that I could use the Pythagorean theorem. Now, I do need to identify where the 90 degrees is. And I can see real clearly it's this angle C. So that's falling into line with the way that we would label our diagram. The 90 is always at C in a right triangle. I can use the Pythagorean theorem here. So I am looking for side AB, which is, in terms of Pythagorean theorem, side C. So I'm going to set it up. A squared plus B squared equals C squared. And I'm just going to plug in my values that I just found for side A and B. So just to identify these, side A is opposite vertex A. So that's got a length of 7 squared. Side B is opposite vertex B. So that's got the length of 10. We'll substitute that in as well. And all that's going to equal C squared. To solve for C squared, I'm going to take the square root of both sides. And I just want to get an estimate then. So the square root of 7 squared plus 10 squared. And we'll take this to the calculator. So square root of 7 squared plus 10 squared is going to be roughly 12.2. So we'll take that back and note it, 12.2. So we'll call it different things here. A, B is 12.2 units roughly. And we'll put it here with our solution because that's what we actually just solved for. It has a value of about 12.2. And then we'll label it here on our diagram, 12.2. So with that, we've solved for all the sides. I'll highlight those in yellow here. So side A had a length of 7, side B had a length of 10, and side C had a length of 12.2. What's left for us to capture are the two angles that are acute angles. So I got angle A here and also angle B. And to find those, I'm going to go back to the sides that were given as exact numbers. So side A was 7, side B was 10. So I'm going to start here. I want to find the measure of angle A. So to do so, we can use a trig strategy we've used in other lessons where I set up a trigonometric ratio and then use inverse function to get back to the angle measure. So here from side A, I know that length of side A is 7. That's opposite vertex A. And then side B is adjacent. So I'm looking for a trig ratio that's opposite over adjacent. And that for me is going to be tangent. Remember, that's the way we define tangent of theta. So we'll say that the tangent of A equals opposite 7 over adjacent 10. And then to capture the angle, I'm going to take the inverse tangent of both sides. And what that will do is cancel the tangent function, and we'll just have A on the left. And then my expression here that was going to actually give me my angle A is inverse tangent of 7 over 10. So I'm going to take that to the calculator, inverse tangent of 7 over 10. And remember, inverse tangent is under the functions tab, middle column. And then I'm looking for 7 over 10. One thing I need to make sure before I take that approximation is to make sure I'm in degrees. So we are there, we're in the correct setting. So the estimate that I would take is about 35 degrees. We'll take that back to our note screen here and finalize 35 degrees roughly. And I'm going to mark that in two places. So I'd started a list here on the right. So measure angle A is about 35 degrees. We had already seen the measure of angle C is 90 degrees. That's our right angle. So what's left for us to discover is the measure of angle B. And again, I could do that in a couple different ways. I could just note that all three of these angles have to add up to 180. So it's going to be 180 minus 90, which is 90. 90 minus 35 should be 55 degrees. Now we can confirm that by going back to some of our trig ratios. So before I do so, let me mark 35 degrees that we just calculated for measure of angle A. And let's confirm for angle B. So B, if I wanted to use the two lengths that are exact, 10 and 7, would be the ratio also opposite over adjacent. But for this one, if we set it up tangent of B, the opposite side for angle B is going to have the measure of 10. So notice the fraction is the reciprocal here. So tangent of B equals 10 over 7. And once I've got the setup, I'll apply inverse tangent to cancel the tangent function on the left. And we end up with this statement that B is equal to the inverse tangent of 10 over 7. So we'd had a hypothesis that was 55 degrees. Let's see if that is consistent. Inverse tangent of 10 over 7. We'll grab the inverse tangent function and give the inverse 10 over 7. Sure enough, that's coming out as 55 degrees. We'll head back to our notes to finalize that one. And with that calculation, we finalize the solution of this right triangle. Just to remind what that means, it means that I've found all three side lengths. Those are the ones that are highlighted in yellow, and all three angle measures. Those are the three highlighted there in green. We have solved the right triangle. Notice our strategy there involved the Pythagorean theorem, and then also this tangent ratio, where we use the inverse tangent to find the angle measure. Our second example takes away from us the ability just to count. Notice that this triangle is oriented to where all the sides are not horizontal, not vertical. They're all at a tilt, some angle. So what I need to do first is just identify the vertices, and then I need to find the side lengths. So I'm going to start by labeling the coordinates of the vertices. So vertex A here has the coordinate -8, -5. Vertex B is at the coordinate 6, 1. And vertex C at the coordinate 2, 5. Now, I've got to use these vertices to find the lengths of those sides. Because none of them are vertical or horizontal, I can't count. So I have to use the distance formula. So let's remember the distance formula. We use it first to find the hypotenuse, side AB here. So I'm going to set it up. Remember, the distance formula is related to the Pythagorean theorem. It's the square root of the difference of my x's, x2 minus x1 squared, plus the difference of my y values, y2 minus y1 squared. So as I set up for side AB, I need to label x2, x1, y2, y1. So remember, those go together. So -8, if I'm labeling A, it's going to be x1, y1. And then side B here, or I'm sorry, vertex B is going to be x2, y2. I label those so that I can just pick them up and not worry too much about how I'm placing it. I've already got the template here. So for the first difference, x2 minus x1 is going to be 6 minus -8 squared, plus 1 is my y2 minus -5. Now those double negatives are going to turn into positives. So this is going to become 6 plus 8 squared. So that's 14 squared. We can go ahead and do some of this calculation here. 14 times 14 is going to be 196. So this is going to be the square root of 196. And then 1 minus -5 is 6. 6 squared is 36. And so what we're really trying to calculate is the square root of, well, let's find the sum. 196 plus 36. It's going to be 232. And then the square root of 232 is going to be about 15.2. And that finalizes calculation here of side AB, 15.2. Let's do some similar calculations then for side BC. So we'll pick up side BC. And I need to label its coordinates. So if I've called B x2, y2, C, I'll call x1, y1. And just like we did for side AB, I want to substitute those values into the distance formula. So for this version, my y2 is going to be 1 minus y1 is 5. So 1 minus 5 squared, plus x2 is 6 minus x1 is 2. 6 minus 2 squared. And that's going to give me the square root of 1 minus 5 is -4. -4 squared is 16. Plus 6 minus 2 is 4. 4 squared is 16. So that's equal to the square root of 32, which should be about 5 or 6 point something, but let's calculate. So square root of 32 is going to be roughly 5.7. Our last side length is going to be side AC. So we'll continue by setting up here with the distance formula. Now I want to relabel C here because I'd already labeled A, X1, Y1. So I'm going to just adjust C to be X2, Y2 for this version. So then for side AC, I'll set up distance formula there. So that's going to be Y2 is 5 minus -5 squared plus X2 minus X1, 2 minus -8 squared. So there's our setup. So this is going to be 5 plus 5 is 10 squared is 100. And in fact, 2 minus -8 is also 10 squared is 100. So that's the square root of 200, which should have the value of about 14. But again, let's get a value here. So square root of 200 is in fact 14.1. And that concludes our side length. So I'm going to highlight those. We'd found all three side lengths. In this case, we use the distance formula. Now, in our previous version, we used the Pythagorean theorem. We could confirm that these satisfy Pythagorean theorem. So just to do so, I'm going to square and add up 14.1 and 5.7. So 14.1 squared plus 5.7 squared is 231.3. What I want to check is, does that roughly equal to 15.2 squared? And that looks pretty good, 231.04. So the difference between those values, if I'm thinking about Pythagorean theorem, is because I rounded these answers here on the right, approximately confirming the Pythagorean theorem that this is a right triangle. All right, so now for our angles, I'm going to identify that the angle here at vertex C is 90. It looks like 90, and it's also confirmed because that is vertex C. And I know that all these are right triangles, so they have to have a 90 degrees in them. So then what we want to do is find out what's the measure of angle A, what's the measure of angle B. So that strategy, we've got all estimated side lengths. So really none of them are going to be better than the others in terms of accuracy. So I'm just going to pick for angle A here. Let's take the opposite side, 5.7, and divide that by the hypotenuse. So remember, opposite divided by hypotenuse is sine. So I'm going to set this up for angle A. Sine of A equals opposite 5.7 divided by 15.2, excuse me, which is my hypotenuse. So then to solve there, I'm going to apply the inverse sine to cancel sine on the left. And my measure of angle A is going to be the inverse sine of 5.7 divided by 15.2. So we just need to record that. Actually calculate it and record it. So inverse sine of 5.7 divided by 15.2. Let's take that to Desmos. I'll locate the inverse sine function under the functions tab. Make sure that's in a new cell there. And then remember our function, or our distances here are 5.7 divided by 15.2. And that's giving me an angle measure of 22 degrees. We'll finalize that one. So angle A we calculated as 22 degrees. Measure angle A equals 22 degrees. And I'll mark that here, 22 degrees. So again, I got some different options because the angles have to add to 180. I could subtract 90, which is 90. 90 minus 22 is going to be 68. So the hypothesis that I've got is that measure angle B should be 68 degrees. But let's confirm it by setting up a last trigonometric ratio. So we'll do sine again here. So sine for B is going to be the opposite side, but opposite from B is 14.1 divided by 15.2, the hypotenuse length. So solution's the same there. Apply inverse sine to cancel sine on the left. And then my angle measure should be given by inverse sine of 14.1 divided by 15.2. So to finalize here, and really we just want to confirm, is that 68 degrees? So what I can do is just pick up that same expression, but just change my numerator to the 14.1, and that gives me 68 degrees. We'll bring it back to our notes to finalize. So B again, measure of angle B is equal to 68 degrees. And with that confirmation, we have solved this right triangle. I had the three side lengths there highlighted in yellow, our three angle measures there in the green. Thank you for joining for this investigation of solving right triangles on the coordinate plane. See you soon.